So our next speaker is James Esdaile from Swinburne again, and he will be talking on the velocity dispersion measurements of massive quiescent galaxies at a redshift between 3 and 4.
Okay, can you hear me? Yeah.
Yes.
Okay, hi everyone, my name is James Esdaile. I'm a PhD student at the Swinburne University of Technology, Centre for Astrophysics and Supercomputing in Melbourne, Australia. I want to thank the organisers for having me and for giving me a talk slot that I can be awake for. So today I want to finish up the conference with quite an exciting result, and that's the kinematics of massive quiescent galaxies at redshift 3 to 4. Right. So the exciting result is that we've made velocity dispersion measurements for 4 massive quiescent galaxies at redshift greater than 3 using the MOSFER spectrograph. And this is the first population measurement that's been made for these galaxies. So there's only been one other measurement of a velocity dispersion made for a quiescent galaxy. And you can see from the very beautiful spectra at the bottom of the screen that the signal to noise is high enough to make these measurements. It takes about 5 to 10 hours of exposure time with Keck and K-band to get the signal to noise. So we're really excited and impressed that we're able to make this, this high precision measurement. So that's the exciting measurement. I'll get into a little bit about what we do with that measurement in a bit. So I just want to go through some background for why massive quiescent galaxies are interesting. And so they're very massive. They're more massive than the Milky Way, but they're about 10 times as small. So they're really very, very compact. And they form rapidly and quench within the first 1.5 billion years of the age of the universe. And so this has been very challenging for theory and simulations to be able to reproduce, both from a mass perspective to produce galaxies this massive that early, but also to quench them. And so evidence for quenching has been seen in the recent years. For example, in Glazebrook et al. 2017, you can see the MOSFER spectrum at the bottom that show strong Balmer absorption features consistent with old cell populations and limited star formation. But from the mass perspective, it's harder to constrain this. So we model by using template fitting and modeling the star formation history and assuming a mass to light ratio as well. And so there's a lot of uncertainties here that can lead towards uncertainties in the mass. But by using the spectra measuring kinematics and also the HSD imaging that we have available in the H-band for these galaxies, so we can resolve the sizes, we can combine all this information to measure a virial mass for these galaxies. And that's what we've done. So this is the first result, is the dynamical mass to stellar mass for quiescent galaxies at various redshifts. In blue, we have it in the local universe. In brown squares, we have redshift 1.5 to 2 quiescent galaxies from the Mendel 2020 sample, and the single measurement of the velocity dispersion for a redshift 4 quenching galaxy in purple, which has an upper limit because they don't have HSD imaging, so they can't resolve the sizes. But we do, and that's the colored circles there. And so what we can see if we plot the 1-to-1 line is that the dynamical mass is actually consistent with the stellar mass. This is really significant because it means that the simulations need to be able to reproduce quench galaxies of this mass. And this really requires dedicated AGN physics to be able to do this. So being able to constrain this is quite important. So that's the initial result, but what we can do is break up these into the different components that go into these dynamical mass measurements and see if there's an evolution that we can see with this population. So this is a size mass plots. We can see that even as early as redshift 3.5, these galaxies are very compact, even more so than the redshift 2 galaxies. And so it's thought that these galaxies will need to evolve in size to become local elliptical galaxies that we see today, but without evolving too much in their mass. And so this is consistent with a minor merging scenario. So if we look at the kinematics, which we can add, we can sort of complete this picture because the kinematics are thought to be stable during minor mergers. And so we can see that there's really a need for an evolution of size in these galaxies. So this is not a novel result. This has been seen in redshift 2 population already, but this is the first time that we're seeing this at redshift 3.5. So this is really exciting. So we can also look at the M sigma plane, and it's a little bit harder to disentangle the two populations, but if we fit the mass sigma relation to the redshift 0 population, fix the slope and scale to the intercept of the higher redshift population, we can see that there's an offset here as well. And then finally, in the dynamical mass, stellar mass plot, again, we can do a similar exercise. And so this is really giving us a holistic picture of size evolution, where these galaxies, compact galaxies at redshift 3.5, are increasing in size and incorporating more dark matter into their central regions and increasing their dynamical mass. So that's the key results that I wanted to go through. We're really looking forward to using James Webb Space Telescope because there's evidence that these galaxies have flat structures at redshift 2 and are rotationally supported. And so by using JWST, we can get not only high spatial resolution images, but try and resolve the kinematics. And given that the dark matter fractions are quite low in these galaxies, we expect that if there aren't rotational supports and that there's a deviation from the dynamical mass to what we expect, that this could be an indication that the IMF varies in these galaxies. So with that, I'll leave you with my summary. We've made the first population measurement of velocity dispersions for massive quiescent galaxies at redshift greater than 3. Confirmed that they are as massive as we expected them to be, and seeing that the size evolution for this population starts as early as redshift 3.5. So thank you.
Thanks, James. A great talk. So there's already a question here in the Q&A. Could you say more about the kinematics, how the kinematics is derived from data, such as what tools you are using and how the uncertainty of velocity dispersion is calculated?
Yep, that's a great question. So we use a software called PPXF, Penalized Pixel Fitting method from Capillary 2004 and 2017. And this is fitting spectral templates and convolving them with various velocity dispersions to try and get a match to the observed spectrum. There are formal uncertainties that are quoted with this software, but we actually randomly resample the spectrum. So we perturb the spectrum by the observational noise and remake the measurement. And we do this thousands of times and get the standard deviation on our return measurements to get a uncertainty.
Muted. Another question here by Brian. I see that at least 2 of the 4 galaxies lie a few sigma below the 1:1 dynamical to stellar mass line, in their stellar mass is larger than the dynamical mass. Was the stellar mass measured in larger aperture than the dynamical mass? Otherwise, how do you explain the excess in the stellar mass?
So just take a look at this population here. So the deviation is quite small. It's within the measurement errors from the 1-to-1 line. There are evidence for a superlinear trend. So that we would expect that from the mass size relationship, for example, that more massive galaxies would have bigger sizes and have more dark matter contents, and therefore their dynamical masses would be higher. And so this should sort of produce a superlinear trend. These galaxies are resolved. So So we're not we're encapturing all the light into our stellar mass measurements, and so there shouldn't be aperture effects that differences between the galaxy population.
And then one last quick question, which was the same as mine, and then the other ones will go into the Slack, which was about the orange point, that it seems to be an outlier to the other galaxies.
Yeah, so as I was just explaining, because this galaxy has a higher stellar mass, it's also likely to be bigger in size. But we do have the size measurement for that, of course. And it's about 6 times larger than the other population. And so we do expect that there is a higher dynamical mass in that population. It's more interesting to see the galaxies that potentially fall below the line, because including dark matter can increase the dynamical mass, but it's harder to decrease the dynamical mass. For that, you know, there could be rotational support, which violates the virial theorem assumption that we use to do the dynamical mass, or it could be an evidence for variation in the IMF.
Okay, thanks, James. And thanks to all of the other speakers in the sessions. If you do have any additional questions, please write them on the Slack to get your answers there.